Hello. In this tutorial, we'll examine how to use the slide rule to take squares and square roots, or cubes and cube roots of numbers. You should already know how to read the C and D scales on the slide rule in order to get the most out of this tutorial. To square a number on a slide rule is a pretty easy thing. You simply locate the number that you wish to square on the D scale and follow up to the A scale using the cursor. So for example, if we wish to square 2, which is a nice easy example, we line the cursor up with the 2 on the D and we look up to the A, which on this model is at the very top, and we find that the square of 2 is 4. If we wish to square 4, let's say, we locate 4 on the D and we read up to the A, and you'll see that the A basically comes in two halves which are identical. The A really is just two half-size D's stuck together. And if you know a little something about logarithms, you might know why that's the case, and if you don't really need to in order to make use of the scales. But this would correspond to, in this case, 10 and 20, and so if I follow these major divisions, there's 11, 12, 13, 14, 15, 16. Of course, the real usefulness of a slide rule is in squaring numbers that are a little bit less convenient. If we wanted to square, say, 4.5, we would locate 4.5 on the D and we would read up to the A, and we would find that it's just a little bit to the right of the 2. So it looks like maybe about a 2, 0, something, maybe about a 2, 0, 2. And if you didn't trust that last digit, you could say, well, 4.5 squared is about 20. As you might imagine, if taking squares involves reading numbers from the D scale to the A scale, taking square roots involves transferring values from the A scale to the D scale. It just runs in reverse. You encounter a slight complication, though, when it's time to take a square root, and that is that if I want to take the square root of 5, I look up on the A scale and I find that there are two 5s, because there are sort of two compressed D scales stuck together to make an A scale, and so I need to know which of the 5s to align with in order to find the square root of 5. To help us with that, it's worth examining the cyclical nature of square roots. If I take a look at the square root of 2, and I just use my calculator to assist me on this, I find that it's about 1.4142. If I take the square root of 20, I find it's about 4.472. If I take the square root of 200, I find that it's about 14.142. If I take the square root of 2,000, I find that it's about 44.72. And what you see is sort of an alternation, where from 2 to 200, the digits are the same, but it's just 10 times greater. From 200 to 20,000, you might imagine that you would see these same digits again with another movement of the decimal place, and so it would be 141.42. And in fact, if you ask a calculator for the square root of 20,000, that's what it's going to give you. And then in the alternate powers of 10, you have this other set of digits. So the square root of 20 is 4.472. If I multiply by 100, it's 44.72. This shouldn't surprise anybody, because in multiplying by 100 under a square root sign, we're basically multiplying by 10. So we just need to keep track of the fact that the power of 10 that's represented, the order of magnitude that's represented in the number that we're square rooting, is going to drive where we look. So if I were to take the square root of 2 on a calculator, I would look for 2 on the left-hand side of the A, and I would read down to the D, and I would find it's about 1.41. If I want the square root of 20, I look on the right-hand scale of the A, and I read down, and I find that it's about 4.4. You can maybe get a 7 out of there. You're not going to get the 2. But about 4.47, and so on. So if I'm taking square roots of numbers between basically 1 and 10, I use the left-hand side, and from 10 to 100, the right-hand side, and from 100 to 1,000, the left-hand side, and I alternate in that fashion. So if I want the square root of 5, I'm going to look at 5 on the first cycle, the left-hand cycle of the A, and I read down, and I find that it's about 2.24. If I want the square root of 50, which as we know is going to have to be a little bit greater than 7, because 50 is just above 49, if I find a 5 on the right-hand cycle of the A and I read down, it looks like it's about 7.08 maybe. You might just want to call it 7.1 for safety. It's worth noting also that because the B scale on the slide is identical to the A scale, one could, instead of working between the A and the D in order to take square roots and squares, one could work between the C and the B and take square roots and squares. And of course, if the slide is aligned with the body of the rule, it doesn't matter. But if you're elsewhere somewhere, sometimes it's convenient to work between the C and the B, depending on the nature of your calculation. Knowing what we do about square roots in the A and the D scales, it might be a good exercise to try to just look at the rule and see if there might be anything that would involve cubes and cube roots. And if you glance over it briefly, you'll find that the very bottom scale in this particular model, the K scale, has 3 cycles of sort of a compressed C and D scale. So it's as though you've got 3 D scales ganged together and then shrunk to a third their size. And given that a half-size scale was good for squares and square roots, it seems reasonable that a 1/3 size scale would be good for cubes and cube roots. And so when we want to cube, we're going to look at values on the D scale and read down to this K scale, which is again at the very bottom. So if I want to cube 2, we'll start with an easy one to which we know the answer. If I want to cube 2, I locate it on the D, and I look down and I find that I'm at 8 on the K, and so 2 cubed is 8. If I wanted to cube something a little more esoteric, like 2.6, I could locate 2.6 on the D and read down to the K and find that I'm at about 15, 16, so maybe about 17.5 on the K. So 2.6 cubed would be about 17.5. If I want to take cube roots, I have to be aware that cube roots follow the same sort of cyclical pattern that square roots do, except they're going to go every 3 powers of 10. So if I want the cube root of 3, let's say, I will locate 3 on the K, on the left-hand cycle of the K, and I will read up, and I'll find that the cube root of 3 is about 1.44. If I want the cube root of 30, I will locate 3 on the middle cycle of the K. And I find that the cube root of 30 is about 3.1, which is not surprising since the cube root of 27 is 3. If I want the cube root of 300, I will go to the right-hand cycle of the K, and I will look up to the D, and I'll find that the cube root of 300 is about 6.7. Then if I want the cube root of 3000, it's back to the first cycle, the left-hand cycle of the K, and then we repeat ourselves. So the cube root of 3000 is going to start with the digits 1, 4, 4, but I need to know that from the context, from the size, that must be 14.4 rather than the 1.44 of the cube root of 3 itself. And that's how you take squares and square roots and cubes and cube roots on a slide.